Hey Year 12, so retrieval roulette, get your books out, pause the video, answer these questions. So here's your answers. Question 9 had asked you to describe a step down transformer, I think. So step down will have more turns on the primary coil and less turns on the secondary coil. If the question was the other way around and it asked you to draw a step up, there'll be more turns on the secondary coil. Okay, so pause, get those marked for me. Thank you very much. Right, last day we started doing the stuff on transformers, and I had asked you to do the questions on 242 and 243. So I'm going to go through those. Okay, so A I had already done last day. That's it there. B, so we've got our primary voltage here is 10. We've got our number of turns in the primary is 100. Number of turns in the secondary is 20, and we're being asked for the secondary voltage. So do you remember the wee trick with this wee equation is that you can write it whatever way that suits you. So because we're being asked in these ones about the secondary voltage, I'm just starting with that. As long as your two secondaries are either on the top or on the bottom, and your two primaries are either on the top or the bottom, then it'll work. Because remember, it's basically ratios that we use here. So to get the secondary voltage, Vs over Vp equals Ns over Np. Next, just fill in my values. So Vs, Vp is 10, Ns is 20, and Np is 100. So that is going to give me 2 volts. It's really annoying me that I'm working across the page here, sorry. C, our primary voltage is 240, our number of turns in the primary is 400, number of turns in the secondary is 20, and we're looking for the secondary voltage. So Vs over Vp equals Ns over Np. So Vs over Vp, 240, equals Ns, 20, over Np, 400. So I'm going to have to go up there here anyway. So 20 divided by 400 multiplied by 240 gets me 12. Okay, over here then, our primary voltage is 4, primary number of turns is 50, secondary number of, oh, I've done that wrong, of turns is 2000, and we're looking for the secondary voltage. So Vp over, I've done that wrong, hold on. Vs over Vp equals Ns over Np. So Vs over 4 equals 2000 over 50. Go back up here then. So Vs is going to be 2000 divided by 50 multiplied by 4, 160. Okay. Now, question 2, I had sort of helped you out with ones like this because whenever it's a wordy question, it can be tricky to figure out which one's the primary and which one's the secondary and all. So calculate the secondary turns. So automatically I should have written down, it's looking for the secondary number of turns. A 3 volt lamp, that means the lamp itself is run on 3 volts. So it's the secondary voltage, and that's going to be run from a 24 volt supply. So that is the input. Didn't put my voltage on now, look. So that is our primary voltage. And there's 480 turns on the primary, and we have to calculate the secondary turns. So because I'm looking for the secondary number of turns, I'm going to start my equation with Ns. It just means I've less rearranging to do. So Ns over Np equals, remember, keep your secondaries together and your primaries together. So it's going to be Vs over Vp. Fill in what I know. So Ns over Np is 480, Vs is 3, and Vp is 24. So Ns is going to be 3 divided by 24 and then multiplied by 480. And that gets me 60. Now, quick checks with things like this. I should have mentioned this already actually. See the way our primary number of turns is smaller that's a lie, that's the voltage. See the way our primary voltage is bigger than our secondary voltage? That means that our primary number of turns should be bigger than our secondary number of turns. So it follows step up or step down wise. Always do a wee check for that. Okay, so for 3A, what material is used for the core? Iron, soft iron. What form of energy? Magnetic energy. Now, why does a transformer not work with DC? I think that was maybe one of your retrieval roulette questions today. No, I just checked back, it wasn't. Sorry, I must have just looked at the question and it whenever I was getting it sorted. Anyway, why does a transformer not work with DC? Direct current produces a steady magnetic field, and the secondary coil needs that magnetic field to be cutting across it to produce the current. So I cut it down a wee bit there. The secondary coil needs a changing magnetic field to produce the current, and with your input supply being alternating, that means your magnetic field is going to be constantly changing, so you're going to be constantly able to produce a current in that secondary coil. Now, number 4, a transformer is used to light a 12 volt 24 watt bulb. So this is our secondary. The primary coil has 1,000 turns, so NP is 1,000. I should label this primary then as well. With an input voltage of 240, so VP is 240. Is this a step up or step down transformer? So even before we've done any calculations, we can tell that because it's using a 240 volt supply, and then this is running on 12 volts. So it's a step down transformer. Now, that is all the questions I had asked you to do last week. Obviously this question does continue over the page, but I left out the wee section on the power, so I'm going to go back to those notes and then we'll continue on with these questions, okay? So go back to 242 for me. Do you remember last day I just didn't want it to be information overload. I didn't want to be bombarding you with all the new information about transformers and then this little bit as well. But see, whenever we're working with transformers, they are very efficient, but whenever we're doing calculations, we assume that they're 100% efficient. They won't be 100% efficient in real life, but for our calculations, that is what we assume. Now, if you remember learning about efficiency, we either calculate efficiency using the useful energy output divided by the total energy input, or power output over power input. So if something is 100% efficient, it means that the power in is going to be exactly equal to the power out, okay? And we're just going to make use of that in questions to calculate either like a missing current or a missing voltage. So we assume that the transformers that we're doing these calculations on are 100% efficient. This means that the electrical power in the primary coil is equal to the electrical power in the secondary coil. This is just a wee reminder about how we calculate electrical power. So power is current multiplied by voltage. So if our power in the primary is equal to our power in the secondary, then IV equals IV. So IV for the primary equals IV for the secondary. Now, some of these questions do make use of that. So what I want you to do now is to give the questions on page 244 a go, okay? So pause the video and do these, and then replay, and I'm going to go through them here with you today, okay? So you need to promise me that you're going to give these a go yourself, right? Right. So if you're watching this bit of the video, you should have done these questions already or attempted them. Right, okay. So I redrew this. This is just the information from the back of the page. I hope I've copied everything correctly, just because I was too lazy to go flicking backwards and forwards all the time. I didn't want to be doing that. So calculate the number of turns in the secondary. So number of turns in the secondary, if I use my wee ratio equation over NP, is going to be VS over VP. So if I fill in all the information I know, NS over number of turns in the primary is 1,000 equals VS is 12 over VP, which was 240. So NS is going to be 12 divided by 240 and then multiplied by 1000. And that gets me 50 turns. Now, part C, calculate the current in the lamp. Oh, I didn't even draw my lamp over here. Here it was. So if I look at my lamp, I've got the voltage and I have the power. So I can use P equals IV to do that. If I rearrange that and make my current be the subject, I get I equals P over V. So the power here is 24 and the voltage is 12. So that's going to get me 2 amps there. State the power delivered by the secondary to the lamp. That's just the 24. So 24 watts. Okay. Part E, if the transformer is 100% efficient, what is the power in the primary? Well, if it is 100% efficient, the power in is going to be equal to the power out. So if it's 100% efficient, the power in the primary is going to be 24 watts. In this case, calculate the current flowing in the primary. So if I look back up here, I have the voltage for the primary. I've just said if it's 100% efficient, the power is 24 watts. My voltage from up here is 240. And I have to calculate the current. So I'm going to use again I equals P over V. Power is 24 and voltage 240. So it's going to be 0.1, isn't it? Yeah. Now, part G. People always do this one the wrong way around. So if the transformer was only 50% efficient, how would this affect the primary current? So see if it was only 50% efficient, then that would mean you would have lost half of your power going from the primary into the secondary. So that would mean that the power here would have been 48 watts because that's double this 24. So my power, if this was the case, my power in my primary, I'm working with everything here, right? And my power would have been 48 watts and my voltage is still 240. So if I now work out what my current would be, and you can probably have done this without doing the calculation, but I always like to do the calculation to prove it. So the power 48 and my voltage 240. So that gets me 0.2 amps. So see what I mean whenever I was saying there, you could probably have done that without doing all this calculation. If it's only 50% efficient, you're going to have lost half of it, so our current would have doubled. But I like to prove it with the calculations. Now, over to page 245. This is it. This is our very last bit of the course, year 12. And you know what? There's very little information that I'm going to give you here apart from what is on the page. So let's work our way through it. So, transformers are used in the transmission of electricity from the power station to our homes. And they're used very cleverly. Look at that typo there. Okay, so it's very clever the way it's used. So electricity is created at 25,000 volts and stepped up immediately to a very high voltage to be sent over long distances. Now, you might think, well, that seems wrong. Why would you want to transfer it at really high voltages? Well, do you remember what we were just saying there? Can't find my notes right here. Transformers are very efficient. They're not 100% efficient. So if we think about the power in is roughly equal to the power out, because power is equal to current multiplied by voltage. If we have a really, really, really high voltage, it means we can have a really low current, and high currents are what are dangerous to us. Also, really high currents will heat up the wires that are transferring the electrical energy. So do you remember me doing that experiment in Mrs. Turner's room and burning the wire because I let the current get too high? If we were to transfer this electricity at a low voltage, it would have a really, really high current value, and you're going to end up wasting an awful lot of energy in the form of heat. So that's why that electricity gets transferred at really, really high voltages. Anyway, I'll go back to the notes now. So later the voltage is stepped down by substation transformers for distribution to homes and businesses. So you're not using the really high voltages in your house. I was going to answer this, but I think the answer is actually here. Why is the voltage stepped up so much to transfer the electricity over long distances? That is just what I was talking about there with the current. And if you were to have a really, really high current, you want to lose a lot of energy. So this is going through like the maths behind that. If 400,000 watts of electrical power has to be sent through cables, it can be done. And this is obviously only 2 examples of this, but like 2 extremes to show you what we're at. It can be done as 400,000 volts at 1 amp, or 400 volts at 1,000 amps. So in other words, if we use the formula P equals IV and the power produced stays constant, the electricity can be sent out at a low current, high voltage, or high current, low voltage, because these 2 are going to be multiplying together to give you the same number. We do not want energy to be lost as heat in the cables, so we want as low a current as possible. If you allow the current to travel at a really if you allow a high current to travel, you're going to lose a lot of that energy. So that's why we send electricity as a really, really high voltage. Okay, so this wee diagram, the type of questions that they do tend to ask with this is that, like, which one is a step up and which one is a step down. So from the power station to the national grid is a step up transformer, because you want to be sending that electricity at a really high voltage, low current. And then to your home, it's a step down transformer. Okay. Now, here's what I need you to do. I need you to do the questions on page 246, 247, 248 and 249. Okay. If you do those and then upload photos or scans of your work, then that'll be us. Okay, I will see you next day.